So here we are on number 3. Now, here's something I'm worried about. I'm worried that some of you haven't even read number 3, and we're just like, oh, videos are up? Sweet, I'll watch those. And then some other ones of you read number 3 and we're like, well, I don't know how to do that. Let's see if the videos are up, but haven't even tried it. That's bad. I think that's the serious drawback of doing these review sessions, be they live or recorded. The point of giving you practice problems or review problem set or practice tests is that you do it, that you struggle with it, that you see the problems that you might run into. If you just watch and say, oh, that's how you do that? Cool. You're lessening your learning. You're lessening the potential to learn in the course of that. You're going to be like, oh, cool, that makes sense. But you never figured out what your question was or what your potential mistake was or your hang-up. You don't know what it is that you need to know about this. You're just kind of following along and being like, that kind of makes sense. And then you get to the test, you've never tried it before, so you don't know what you're going to do wrong. Don't do that. But I'm worried that some of you don't know what this means. So I will tell you what this means. Let's go ahead and walk through. What is this telling us to do? Well, it's saying that there's 4 moves: squaring, dividing by 2, adding 3, and subtracting 4. In some arrangement, some composition or recomposition, some arrangement of these moves makes this function, x squared over 2 minus 4x plus 11. Well, let's just say, okay, what might an answer look like? What does it mean to answer this question? Let's say we didn't have any imagination and we guess offhand that the answer is A of B of C of D of X. Clearly that's not the answer, but let's say that's what we guess. Okay, well, what would we have gotten? A of B of C of D of X is, well, it's a way of looking into all of these. It means we have to take D of X, input it into C of X, input that into B of X, and input that into A of X. So just C of D of X would be, well, I look at C, which is x plus 3, and I input D of X into that. So it would be x, oh, but I'm not going to write x plus 3. I'm going to substitute the x with x minus 4. So it's x minus 4 plus 3. Well, what would B of C of D of X be? B of C of D of X would be taking this and inputting it into B of X. So it would be x minus 4 plus 3 all over 2. And then what would A of B of C of D of X be? A of B of C of D of X would be taking this, B of C of D of X, and plugging that whole thing into A of X. So that would be x minus 4 plus 3 all over 2 squared. So we could check and see, okay, does that make the x squared over 2 minus 4x plus 11? We can see that it doesn't. We can see pretty clearly that this is kind of a problem, right? Why are we minusing 4 and then plus 3? Those are just going to undo each other. Like minus 4 plus 3 is just going to be x minus 1. Clearly there wouldn't be 2 separate moves if they just undo each other. Anyway, this is not the right answer. But I think it makes it clear what an answer would be and how you go about figuring out what the answer you've tried out is, right? If I wanted to know what is A of B of C of D of X, it means I take D of X, plug it into C, D of X into C. Then I take what I've got, C of D of X, and plug that into B. Then I take what I've got there and plug that into A. So some correct order of doing that is the answer. Now, for those of you that have not arrived at a solution, or even worse, not tried it, stop watching this video right now. I mean it. Get off, pause it, close it, look back at the paper, and try it. Try thinking about how you could work this problem, how you could make sense of it. Don't watch anymore. Really, get off. You get off. stop. Okay, now that I'm only talking to people who have really struggled with this problem, thought about it, or come up with a viable solution, let's talk about how we might go about solving it. So, a couple people solved this in class, and both the people I talked to who solved it in class solved it just by kind of guessing and checking and looking at just this form, x squared over 2 minus 4x plus 11, and kind of doing a little bit of thinking about how it could work, and there's only so many combinations, etc., etc. That's way cool, and if you can do that, that's great. For me, I see this, I'm like, I don't know what moves happened here, right? They're hidden. I want to make clear the transformations that occurred from, I'm guessing, x squared, right? That's the parent function. I see that happens. That's the parent function here. What transformation occurred to take x squared and get it to here? So that's something I want to know. So I'm going to try and rearrange x squared over 2 minus 4x plus 11 and see if I can't mangle it into some other different form. Now, for those of you who had Algebra 1 and Algebra 2 and remember some of it, what I'm doing here is I'm going to take this is the standard form, right? ax squared plus bx plus c. I'd like to see it in its vertex, its transformational form. A times x minus h squared plus k, right? I'm taking this and I'm going to get it into this. Because just by looking at it, this one is going to show me what moves. What's the transformation to the right, what's the dilation, and what's the transformation up or down, right? This would show me all the moves. This doesn't. This doesn't. Now, again, for those of you who remember Algebra 1 and Algebra 2, the way I'm going to do that is this totally cool process called completing the square, which, when we get to conics, is going to come up, again, with a vengeance. So, it's just as well we look at completing the square right now, even though you certainly wouldn't have to complete the square on tomorrow's test. Quiz, retake, assessment. Let's call it an assessment. Anyway, here's how I'm going to complete the square. First of all, I'm going to pull out that dilation factor, the 1/2. So I'm going to say 1/2, get out of there. Now I've got x squared. I'm going to factor the 1/2 out of the 4, and that becomes 8. And out of the 11, that becomes 22. Cool? Cool. And now I want to say, okay, what would be the perfect square? I want to make a perfect square with a minus 8 in it. So off to the side here, I'm going to think, well, what could add up to 8? Well, negative 4. So I'm going to say I would want to make x minus 4 squared. That's something I want to get, because x minus 4 squared is x minus 4 times x minus 4, and that's x squared minus 8x plus 16. Well, I don't have plus 16, but I do have minus 8. The minus 8 is what I can't change. The 16 I can kind of rearrange, right? So I'm going to write here 1/2 times, and I'm going to say, okay, yeah, I'm going to do this step by step. Minus 8x, and now I know I want to have a plus 16, but I can't just go adding pluses 16s everywhere. So at the same time, I'm going to say minus 16 plus 22. Pretty cool, right? Yes, totally cool. Now, this is the perfect square I've made. So I'm going to pull that out separate. So now I've got 1/2 times x squared minus 8x plus 16. And then minus 16 plus 22 is 6. Plus 6. And now I'm going to go ahead and redistribute that 1/2. Once to there, and once to there. Again, I'm keeping isolated this perfect square I made. That's what I wanted to make, because it made this beautiful perfect square, which you can see that beautiful perfect square is going to become a part of that transformational form that lets me see what the steps are. So I'm going to show, all right, this is the perfect square. I'm going to distribute the 1/2 to that and to the 6. That's not part of the perfect square. So now I've got 1/2, my perfect square, x squared minus 8x plus 16, and 3, because I distributed the 1/2 to the 6, and I got 3. Ooh, now I've got it set up well. This x squared minus 8x plus 16 is x minus 4 squared. I just showed that over here. X minus 4 to the second power is x minus 4 times x minus 4, which is x squared minus 8x plus 16. So I'm going to take this and replace it with this, because they're the same thing. So now I've got 1/2 times x minus 4 squared plus 3. And this is another version of f of x. Except for it's an even cooler version of f of x. It's the version that shows me the moves that were taken to transform f of x out of the graph of x squared. So once I know that, it makes it way easier to see the set of compositions. So I see f of x equal to 1/2 x minus 4 squared plus 3. Well, now I can go, okay, what was the original instruction here? Consider the functions. Let's see. I have x squared, x over 2, x plus 3, and x minus 4. Well, what's being squared? Just the x minus 4 is being squared. So obviously it must start with d of x. That's the innermost thing, and that gets squared. So the squared part here is a of x. So I must be squaring d of x. D of x is going in and getting squared. Cool. Then just that part is getting multiplied by the 1/2. So after I plug d of x into a of x, that's getting plugged into the 1/2 part. So it must be b of a of d of x. Then, last thing that happens is we add 3. That's the very last thing that happens, and all of this is going into the plus 3 function. So c of, nice big brackets, b of a of d of x is the composition of the 4 functions, which would result in this, which would result in that. C, B, A, D is the right answer. So we're about to go in Desmos, but before that we have some guest speakers.
Hello, it is I, Brian Mathmaster Dwar.
And Benjamin Soma.
Buenos dias, ¿cómo estás? ¿Cómo estás? Muy bien, gracias, I'm out of here,
That was beautiful. Thank you guys. I think that really added to the depth of understanding there. Anyway, again, you will not be allowed to use Desmos on the upcoming assessment, but it is a great tool for visualizing what's happening. So here in Desmos, I've graphed a few things to show you. I've started with the graph of just the parent function x squared and the function we were discussing, f of x equals x squared over 2 minus 4x plus 11. Now, obviously, if you had Desmos to try to answer this problem, you probably could have just looked at it and like, oh, over 4, up 3. Those are probably the transformations that need to happen. I'll make the x minus 4 inside the parentheses. That'll be my first thing, to go over 4. And then I'll make the plus 3 at the end to make it go up 3. But you didn't, so you had to actually work out the 4 and the 3 and where they went into the function by completing the square. You probably also could have found the vertex if you remembered a little moment in Algebra 1 where they said that the vertex of any parabola lies at negative b over 2a. That would have been another thing you could have done. But anyway, here we are in vertex and we're illustrating what happened here. So I went ahead and I graphed all of those transformations, the x over 2 dilation, the x plus 3 dilation, the x minus 4, translation, and the x minus 4 translation. but we don't really need to look at those because they kind of get in the way. I want to start by saying, okay, the innermost thing we were looking at was d of x, x minus 4. But then right away we went to a of d of x, and then we get a parabola. So the x squared, the blue function, became the green function by a transformation right 4. And that's what occurred in a of d of x. And then b of a of d of x adds in this dilation issue. B of x is dilation by a factor 2. So here you can see we're dividing all the y coordinates by 2. Any given point on the first green function, like 2, 4, drops down to 2. The y value becomes half as large. There's, am I missing it? 2. Great. Then, after we do b of a of d of x, the last function that takes it all the way up to the place we were trying to get, the red function, is c of b of a of d of x. And because that c of x function is a movement up 3, the whole green function here at b of a of d of x moves up 3 and goes to c of b of a of d of x, which is f of x. So the composition of b, c, d, and a in the order c of b of a of d of x forms f of x. Now, just because I think it's kind of fun to view things in Desmos transformationally, here I've added in a little animation where we can see if we took the original function, just x, the identity function, we can see how each of these pieces, a, b, c, and d, work to form f of x. So I'm going to start by saying the innermost thing that happened was that the d value transformed the graph. And notice here that, again, because I'm working with an identity function, we could think of this as being to the right 4 or down 4. Minus 4 with the identity function is equally well expressed by the down 4, the vertical translation of the y values down 4, or right 4, the horizontal translation of the x values to the right 4. But anyway, whatever happens, d moves the identity function to the right 4, which is eventually how that's going to be expressed in this case. And then it gets squared by a. So we're going to watch as a squares. So that line becomes a parabola. Sweet. Then we know that the next piece that happens is we dilate about the x-axis, which means that all the y coordinates, in this case, because it's x over 2, we're dividing by 2, all the y coordinates get half as large. So here we are, there's that dilation viewed dynamically. And then lastly, we have a translation up 3. The c value moved the graph up 3. And there's dynamically illustrated that up 3 movement. So those are multiple methods of visualizing or seeing how the composition A, B, C, and D in the correct order, C of B of A of D of X, yielded the final function f of x.